I'm happy to say that my medical procedure went fine yesterday. No serious problems, except expect to put up with pain for a while. So what? How was the booster quiz? No comments. Well, the opportunity was there to add a considerable amount of money, student points, that's money, to your score for exam 1. We'll see how you fared. I'll put up the key soon. Now, before we proceed with the analysis that we were considering at the end of our last gathering, which was the solubility of calcium carbonate in a water solution system buffered at pH 8, let's talk about the salt effect. You've recognized that chapter 19 is really divided into 5 categories, or subtopics if you wish. We already looked at the first topic, or subtopic, which were cases where solubility for a salt of limited solubility in water can be calculated strictly from KSP. Why? Because the component ions of the salt show no measurable or appreciable Bronsted-Lowry acid or base properties in water solution. So if you were to recognize or be able to recognize this property for a salt, what would you do? Well, would you look at the component ions of the salt? Would you recognize that we reminded you that the principal example of salts, or principal types of salts, whose solubilities cannot be calculated reliably from KSP, are salts which contain an anion component that are bases stronger than water. So if you can recognize what the ions are, the ions of which the salt are composed, which you should be able to do, look at the acid-base table. See if the ion in question is there. And see if it's got a Kb value, which is larger than Kb for water. And take it from there. That led us to subcategory B, where we're talking about solubility of salts like calcium carbonate, for which you cannot calculate correctly solubility from simply KSP. You need to pay attention to the Kb value for the component ion. Pardon me, the component anion, which for calcium carbonate is, of course, carbonate ion. So before we return to that issue, let's jump to subtopic C, which is not a chemical effect. It's an electric effect, a Coulombic effect. Salt effect is what it's called. To illustrate, the solubility of silver chloride in deionized water. We talked about that first thing in chapter 19. Solubility of silver chloride in deionized water is simply the square root of KSP for silver chloride. Pretty simple regarding solubility determination. What if we try to observe, or in fact observe, the solubility of silver chloride in 1 molar sodium nitrate solution? In which of these systems, deionized water or 1 molar sodium nitrate solution? In which of these systems will the solubility of silver chloride be greater? Or is it the case that the solubility of silver chloride is the same in each system? Well, number one, the solubility of silver chloride is much different, this system versus this system. Number two, observations of solubility, making measurements from experiments in the laboratory, would show us S silver chloride is much greater in the sodium nitrate solution. Well, much greater. That certainly tells us that neither sodium ion nor nitrate ion foster precipitation of silver chloride. In fact, the presence of high molarity sodium ion plus high molarity nitrate ion is to make the silver chloride much more soluble. Why is that? Well, coulombically speaking, what do we know? Oppositely charged particles attract. Nothing fancy about that. What's the effect of that electrostatic property of oppositely charged particles on the solubility of silver chloride in the sodium nitrate solution? Are the sodium ions going to be attracted to the chloride ions just because they're oppositely charged? Yes or no? Well, come on, Coulomb. Oppositely charged particles attract. You betcha. Are the nitrate ions going to be naturally attracted to the silver ions because they're oppositely charged? Absolutely. Now, does nitrate react with silver ion to make a precipitate? No. The sodium ion react with chloride ion to make a precipitate? No. Well then, what is the result of this non-chemical impact of attraction of nitrate ion to silver ion and sodium ion to chloride ion? And in addition, realize, while nitrate ions travel towards silver ion, are sodium ions going to travel along with the nitrate ions? Are sodium ions going to travel along with the nitrate ions toward the silver ion? As sodium ions are attracted to chloride ion, will nitrate ions travel along with the sodium ions as they travel toward chloride ion? Are sodium ions and nitrate ions oppositely charged? Yes. And in this solution, by far, the most abundant ions are sodium ions and nitrate ions. So here's this cluster of nitrate ions traveling toward silver ion along with sodium ions. And here's this cluster of sodium ions traveling toward chloride ions along with nitrate ions. Well, this winds up wrapping a sheath, enveloping the silver ion with this cluster of nitrate ions and sodium ions. Same for chloride ion, surrounded by sodium ions and nitrate ions. That sequesters silver ion and chloride ion from each other. Because the only way this stuff can form is for this ion to collide with this ion and vice versa. Well, when these sheaths of ions wrap around sodium ion and chloride ion, does that make it easier for does that make it easier for silver ion and chloride ions to collide and make silver chloride, or does it make it more difficult? More difficult. Well, what does that do to the solubility of silver chloride? Increases. That's the salt effect. All done. That's it. It's a chemical effect. Pardon me. A physical effect, not a chemical effect. I mean, it's kind of like, I suppose, if we could wrap automobiles in big thick pads of foam rubber versus automobiles as they presently stand, not being wrapped in big thick pads of foam rubber. Automobiles at 50 miles an hour. Boing! Automobiles at 50 miles an hour wrapped in big thick pads of foam rubber. Boing! Where's the collision going to be much more severe? You know the answer to this. You've probably had pillow fights with brothers and sisters and friends. You ever have rock fights? A little different. So we go back to this. And we reminded ourselves, by paying attention to the chemistry of the system and recognizing that carbonate ion is a base, and knowing that calcium carbonate saturated in deionized water gives a solution pH of 10.0, if we buffer the system at 8.00, we have a solution which is not acidic, but it's 100 times more acidic than pH 10. And the more acidic a system, the more effectively you murder any bases in the system, which are bases that are stronger than water. And you can't make calcium carbonate if you murder carbonate ion. So by murdering carbonate ion more effectively at this system, which is 100 times more acidic than deionized water saturated with calcium carbonate, we've got to make calcium carbonate more soluble in this buffered system. That's the kind of stuff that you have to do first before you start wrestling with calculation. Because at least now you'll know what the intention of your calculation is aimed at. If you've got the 1.4 times 10 to the minus 4 molar solubility data point for calcium carbonate in deionized water, and do some analysis of this system, where you wind up with a solubility that's equal to or less than 1.4 times 10 to the minus 4 molar, I don't give a damn what calculations you did, they can't be right. Because you've come up with an answer which is flatly in disagreement with the chemistry of the system. Now, understanding the chemistry of the system, that's the hardest part. I'm sympathetic with you. That's the hardest part. But that's what chemistry is all about. And so that leads me to a comment about 2045. I've told my colleagues this many times. The problem with 2045 is you are not teaching these students any chemistry. They come to me in 2046, they don't know any chemistry. They've heard about electronegativity, but they have no idea what it means chemically. They know about writing Lewis structures, but they don't know about interpreting the Lewis structures to get at bond angles and important properties of species such as. You're not getting any place with this kind of stuff. Well, never mind that for now. Because one of the intentions and aims of our gathering is to fill in the gaps of the stuff that you should have gotten but didn't get from 2045. We have to do it. So here's the equilibrium reaction we've chosen to consider to get at the solubility of calcium carbonate in our water solution buffered at pH 8 system. This reaction we've recognized as a composite of calcium carbonate dissociation reaction into calcium ion and carbonate ion, for which the equilibrium constant is Ksp, and Kb carbonate ion, where carbonate reacts with water, and by hydrolysis, that just means reaction with water, gives bicarb ion and hydroxide ion. So we put those two reaction equations together to give us this reaction equation. And recognized, be careful with this reaction equation because it is not stoichiometric as written. If you think this means for every mole of calcium carbonate that reacts, you put in solution a mole of calcium ion and you create a mole of this and a mole of this, that's wrong. Because we've recognized that when calcium carbonate saturates in water, a considerable quantity of the carbonate ion remains as such. This reaction accounts for the carbonate ion which didn't remain as carbonate ion. This reaction doesn't have carbonate ion in it. It's not carbonate ion by itself. So, whatever the molarities are of this versus this versus this. The molarity of this, based on this reaction alone, the molarity of this has got to be larger than the molarity of this and the molarity of this. If all we did was to put calcium carbonate in water. Now, last time we calculated K. Here's the K expression. Here's the K value. We recognize that calcium ion, when it goes into solution, stays as such. So if your task is to calculate concentration for calcium ion, solubility for calcium carbonate, what you need to do is calculate calcium ion concentration, or in some fashion determine calcium ion concentration. Because that will be the solubility of calcium carbonate. Since the system is buffered at pH 8.00, here's the hydroxide ion molarity. So the remaining part of this puzzle is to see how the molarity of bicarb ion, which I have represented by question mark, relates to S. So I wrote that here. We know S is this, and we know S as well as this, the calcium ion molarity, is equal to this term sum, this sum. Does this look like MB for carbonate? Material balance for all viable forms of carbonate. So if we start with bicarb and recognize, based on how material balance is defined, what forms of a species can exist in measurable concentration in water solution as a consequence of H plus gain or loss. This you got to know. This we offered you early on in chapter 18. So we're now needing to apply that issue, that consideration to this issue. Bicarb ion loses H plus, you make carbonate ion. Bicarb ion gains H plus, you make this. That's it. Those are all the possible forms, the viable forms of carbonate-containing species in water solution. So to get at the relationship of question mark to S, we want to see how the molarity of this compares to the molarity of this, and we want to see how the molarity of this compares to the molarity of that. Well, we know from chapter 18, this is a conjugate acid-base pair. Acid-base. This is a conjugate acid-base pair, except now this is the acid. This is the base. So we need Ka for bicarb and Kb for bicarb. So here they have been written. There's the Ka value, there's the Kb value. So all I'm going to do, in order to see how S relates to question mark, how the solubility of calcium carbonate in our system buffered at pH 8 relates to the bicarb concentration, I'm going to see how the bicarb molarity relates to the carbonate molarity from Ka, and how the bicarb molarity relates to the quote-unquote H2CO3 molarity from Kb. You can write the K expressions if necessary, and then rearrange them to get these forms of such. Nothing fancy about this. From an algebra standpoint, this is as simple as pie. But a lot of times you folks stumble with this because you're familiar with looking at X and Y. But you're not familiar with looking at bicarb and carbonate and stuff like that. Remember the story I told you about my algebra teacher? Everybody knows X and Y. They don't know X and Y any more than they know the man in the moon. But they were at ease looking at X and Y. And when she gave them the same damn test with A replacing all X's and Y being replaced by B's, all the unknowns now A and B, kaput, they fell apart. That's the way we react. And I'm trying to get you past that barrier. So, at pH 8, for which the hydronium ion concentration is this, divided by Ka, our analysis shows that the bicarb molarity compared to the carbonate molarity is 210 to 1. And for the Kb consideration, the bicarb molarity compared to the H2CO3 quote-unquote molarity is 42 to 1. What's this mean? What do these ratios mean? What do you mean chemically? This ratio means if you are able to exist as a spectator ion, and you buy a ticket to this contest, and you go jump in the beaker where this equilibrium system lives, each time you'd see a carbonate ion. 210 times you'd see a bicarb ion. Or put another way, on average you'd have to look at 211 ions before you saw a carbonate ion. Second case, for every H2CO3 molecule you'd see in there, you'd see 42 bicarb ions. Does it sound like bicarb ion has certainly established itself to be by far the principal form of carbonate in this system? That's it. Consequence? Practically speaking, for this system, calcium carbonate saturated in water system buffered at pH 8, how does question mark relate to S? Practically speaking. They're the same. Practically. So, I go back to this. I take away question mark. I write in S. I got now one equation and one unknown. It's really very simple. S squared is 1.3 times 10 to the minus 6. You agree with that? So S is the square root of 1.3 times 10 to the minus 6. What's the square root of 10 to the minus 6? What's the square root of 1.3? Well, 1 squared is 1. 2 squared is 4. So the square root of 1.3 is a hell of a lot closer to 1 than it is to 2. What's 11 squared? 121. I'm curious. In grade school, or perhaps in high school, did you learn the squares of numbers up to 25? You didn't learn that? I don't get it. This is valuable stuff. If you know the squares of numbers from 1 to 25, then oftentimes, quick and fast, you can approximate the square roots of numbers, which are from the range of 25 squared on down to 1. What's 25 squared? 625. This is valuable stuff. It helps you. I mean, some things are just worth memorizing. In your case, UFID, Social Security number, your last name. You get a job. You go to the pay window, and the paymaster who's got the checks says, "What's your name?" Ring up mom and dad. What's my name? It's clumsy to go through life like that. Learn the squares of numbers from 1 to 25. If you didn't do it when you were supposed to have done it, it's not your fault. It's these stupid people who don't know what the hell they're doing in math classes anymore. I'm serious about this. I did tell you, I believe, our language is two-part, isn't it? Alphanumeric. Have I told you that? Our language is composed of words and numbers. Alphabets and numbers. And do you think it's important to be able to speak the numbers fluently in science class? Absolutely. That's why if you, for example, take 5 times 7 and tell me it's 35, and take 5 times 0.7 and come unglued, something's wrong. Something's seriously wrong. 10 to the minus 2 times 10 to the plus 5. If you've got to put that in a calculator, something is wrong. You have not learned the fundamental language of numbers. Learn it. If you need to learn it, learn it. $11 squared is 121, and 12 squared is 144. So 1.1 squared versus 1.2 squared. Which one is closer to 1.3? Done. Now, do you remember the molarity for calcium carbonate saturated in water? 1.4 times 10 to minus 4. I wouldn't expect you to remember that, but I would expect you to remember that we have used that value before, and it is available for you if you want to look it up in your notes. So, this number compared to 1.4 times 10 to minus 4 is showing you, number one, that calcium carbonate's more soluble in this system, which it has to be because the system is more acidic. And if you take a ratio, you'll find out it's about 8 times more soluble. But is calcium carbonate still pretty soluble? Whoops. Is this a fairly large number? Is calcium carbonate showing itself to be fairly soluble at pH 8.00? That's not a big number. On the order of 1,000th molar solution you've produced. Okay? Now we're going to ask a question. And shortly hereafter, we're going to analyze this system based on this question. But we now have the data on the board that's necessary to wrestle with this. So let's talk about this system in brief right now. Let's consider saturating calcium carbonate in a water solution buffered at pH 6. Solubility going to be ever so larger? When we go from pH 8 to pH 6? Solubility going up? Is the solubility going up? Is the system getting more acidic? Yes. Then the damn solubility's got to go up, because you're killing carbonate ion all the more. Right? The more acidic the system, the more effectively you murder any base species which is a better base than water. And carbonate certainly fits in that category. That's what you got to realize first, because that's the chemistry of the system. So before we analyze this, we already know what kind of answer we're looking for. An S value, which whatever it is has got to be larger than this number. Now, look at these ratios. And when you look at these ratios, I want you to look at the same time, this material balance statement for carbonate or bicarbonate or H2CO3, doesn't make any difference. MB for carbonate species. At pH 8, this doesn't matter, this doesn't matter, this matters. Now let's go to pH 6. Before we do any arithmetic, before we even re-examine these ratios, at pH 6, is this going to matter? This is the best base up here. So if this thing doesn't matter at pH 8, it sure as hell doesn't matter at any pH that's lower than 8. Look at this ratio. What does this ratio become at pH 7? What's this ratio at pH 7? This is the ratio at pH 8. What's this ratio at pH 7? 2100 to 1. Then we make the hydronium ion concentration 10 times greater. So what's this ratio at pH 6? 21,000 to 1. See, you've got to talk the numbers. I don't care about carbonate at pH 6. pH 8, I don't care about it. I really don't care about it at pH 6. Right? Just telling us. But now let's look at the other ratio. And even without looking at the ratio, you know from chapter 18, if I take any system which can contain forms of carbonate, as I make the system progressively more acidic, if I started with this, I'm going to this, and then I'm going to go to this. But if I make the system progressively more basic, I'm going this way. Right? Basic, this is happy, this is killed, this might be killed. Acidic, this is happy, this may be happy, this is dead. So let's look at this ratio now. What is this ratio at pH 6? I'm going to leave the 1 on the bottom. Then we'll put down what you said. What does this number become? What's this become? 0.42 to 1. Correct? pH 6, this becomes 1 times 10 to the minus 8. So this value gets divided by 100. There we have it. And if I want this written with whole numbers, I'm going to take this expression and turn it over this way. Because what I've now shown is that at pH 6, what is the predominant form of carbonate containing things? It's hydrated CO2. This is telling me that practically, when I see one of these, when I see one of these, if I read this as a percent, if I see one of these, and keep, every time I see one of these, count them up. When I see 42 of these, 42 bicarbs, In this system, when I see 42 bicarbs buffered at pH 6, how many H2CO3s am I going to see? If I see 42 of these, how many of these am I going to see? How many? How many? 100. If I see 42 of these, I'm going to see 100 of these. You've got to let these numbers talk to you. Otherwise, there's nothing but a big cloudy mist in front of you. So, before I do any further analysis of this system, I now know that the predominant form of carbonate-containing stuff in the pot is H2CO3. And I have to pay attention to that when I go about the business of calculating this. Now, before we in fact tackle that, let's go to subtopic 4 in chapter 19, which is a direct parallel to what you folks are doing in 46 laboratory. In assignment 2, you learn how to make precipitates of potassiumine and ammoniumine. Cobalti nitrite ion precipitates potassiumine and ammoniumine. Very few anions will precipitate potassiumine, ammoniumine. Very few anions will precipitate sodium ion. One such is uranyl acetate anion. But uranyl acetate contains uranium. And so the EPA types don't want us to use that anymore. However, to the best of my knowledge, no student in the history of using uranyl acetate to precipitate sodium ion has yet been hurt. We do funny things in this country. Really. Funny things. I once had a student call me and complained about the dangers of the general chemistry teaching laboratory. This student was in 2045L. Hadn't gotten to 46L yet. He must have been in horrors when he got to 2046. Because in 2045L, he was asked to do an experiment which involved him handling a few milliliters of 1 molar hydrochloric acid solution. Really concerned about the potential danger of this 1 molar hydrochloric acid solution. Wanted me to discontinue its use in the laboratory. And I said, what do you think is more dangerous? Our students using 1 molar hydrochloric acid solution in the laboratory, or automobiles traveling down the road at 60 or 70 miles an hour? You know how many traffic fatalities occur every day in this country? How many traffic fatalities involve pedestrians walking across the street, maybe jaywalking, maybe it's their fault, they get clobbered, or maybe it's not their fault, the driver's reckless. I said, if you really want to save lives, I want you to ban the use of automobiles. Then you come back and talk to me about using 1 molar HCl in the general chemistry laboratory. Because I know of not one example, not one, of a student ever having been hurt as a consequence of using 1 molar hydrochloric acid solution in the laboratory. I know of not one example of a student going in there and saying, looks good, blah, 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 blah. I mean, when you subtract common sense from the human equation, you lose. That's it. The game is over. And a whole lot of that is going on in our world right now. We have legislation upon legislation upon legislation upon legislation. All because people leave common sense out of the equation. This is not good, folks. So in the main, or one of the things that's certainly in the main, is I hope when you go away from this gathering, you'll have a much better feel and passion for how better life is when you apply common sense and think sharply and clearly. That's what it's all about. If we try to fix every damn thing by making new laws every day, we're going nowhere. And that's exactly what the hell we're doing. And that's horrible. You cannot cure stupidity by making laws. You can't fix it. You can only cure stupidity by thinking. And on occasion, forcing yourself to wrestle with questions that you may not like. But you better wrestle with them if you want to be successful. All right, enough of that sermon. We'll go back to this. Again, you've recognized that ions, should they be present or absent in a solution, can be found by attempting to precipitate that ion. We talked about assignment 2. When you go to assignment 3 in the laboratory and you look in a very penetrating fashion at the water chemistry of calcium ion, you really studied the chemistry of calcium ion in assignment 346L in the presence of 4 other ions. What were these 4 other ions? You studied the chemistry of calcium ion in the presence of 4 other ions. That's mainly what you did in assignment 4. What were these 4 other ions? I'm now asking you if you are immediately familiar with what the heck you're doing in laboratory. How many of you are through assignment 3? You're finished with it. Well, how many of you are presently in assignment 3? All right. So you should all be familiar with this consideration. Did you study the chemistry of calcium ion in the presence of chloride ion? Did you remember, or do you remember, that the calcium ion source that you used in assignment 3, was half molar calcium chloride solution? Half molar calcium chloride solution. Are you going to successfully test for calcium ion's presence or absence in water solution by precipitating it as the chloride? Hell no! It's half molar. This stuff is really soluble. So after you use your calcium chloride solution and did some flame test investigations, then you pursued the matter of, what does calcium ion do if I put hydroxide ion in there in appreciable concentration? And you found out calcium ion and hydroxide ion molarities are high enough you can make a precipitate, a white crystalline solid, calcium hydroxide. Then you put calcium ion in the presence of carbonate ion. Wham! And you make teacher's favorite weapon. And then you put calcium ion in the presence of sulfate ion in an attempt to make gypsum, calcium sulfate dihydrate. Are you familiar with gypsum? Are you familiar with wallboard, plasterboard, sheetrock, whatever name you want to call it? How many of you have ever done work with sheetrock? So, I've built walls. Not hard to do. Is sheetrock particularly soluble in water? Would you like to make walls in your home out of a substance which was fairly soluble in water? You want to make your walls out of sodium chloride? You want to make your walls out of sugar? Here you are, a little kid. You slop your crayons or make a mess on the wall. So mommy comes along, gives you a whack on the hiney, and you traipse off, and then she picks up her sponge and goes to clean off the mess you made. Oh my God, my wall dissolved. It's made out of sodium chloride. You don't do that, do you? So you know calcium sulfate dihydrate, the main ingredient in sheetrock, the main ingredient in casts. How many of you had the misfortune of wearing a cast? Me too. There's sheetrock, calcium sulfate dihydrate. Interesting, isn't it? You see this water here? In sheetrock, in gypsum, stuff you make by adding water to plaster of Paris. 2 moles of water for every mole of calcium sulfate. This is showing you something. Water by itself, under these conditions, is present principally in what phase? You want me to show you? Liquid, right? And some vapor, but no solid. Water in sheetrock is present in what phase? You folks who have made walls with sheetrock, you see the walls crying? You see tears running down from the walls? Hell no! Chemistry's neat. You put water in sheetrock, this is solid phase stuff. That's interesting, isn't it? And we're going to talk about a lot more interesting chemistry like that as the term proceeds. But I want you to get more familiar with these formulas in regard to what they're telling you. We talked about what this tells you. Okay, detection of ion by precipitation. Let's look first at calcium sulfate because it's the simplest of these cases. Let's see why. There's the dissociation equilibrium for calcium sulfate and water. It shows calcium sulfate coming apart into its component ions. So by definition, the equilibrium constant for this reaction is KSP for this stuff. I'll write in here sheetrock. Question: can I calculate correctly the solubility of calcium sulfate in water by using this expression alone? I'll ask the question again. By using this expression alone, KSP, can I calculate successfully, correctly, the solubility of calcium sulfate in water? I heard no's. And that's all right, because I'm betting that the people who said no recognize that sulfate ion is a base which is stronger than water. So you're concluding that I have to pay attention to the hydrolysis of sulfate ion. Is that fair? Let's take a look at the hydrolysis of sulfate ion. Hydrolysis products. Hydrogen sulfate ion, the conjugate acid of sulfate ion, and hydroxide ion. Because this is a base. Clearly then, when it reacts with water, it's got to make hydroxide ion in one of the products. K for this, by definition, is Kb sulfate. We know this stuff. It's all chapter 18 again. And how do we get Kb sulfate? Yeah. We look up Kw. I mean, pardon me, you don't look it up. We know what it is. Kw, pardon me, over Ka for hydrogen sulfate ion, I'll write the condensed formula, is 1.0 times 10 to the minus 14 divided by 1.2 times 10 to the minus 2. What's the gee whiz result of this? This is about 1 divided by 1. So the gee whiz result of this is on the order of 10 to the minus 12. Now if you do the arithmetic, you'll get 8.3 times 10 to the minus 13. Look at the size of that Kb value. Is it big? Kb carbonate, 2.1 times 10 to the minus 4. Kb sulfate, 8.3 times 10 to the minus 13. 2.1 times 10 to the minus 4. How does 10 to the minus 4 compare to 10 to the minus 13? That's like Jupiter next to a P. I mean, there's no comparison, practically, other than to say the strength of carbonate ion as a base is enormous, huge, compared to the strength of sulfate ion as a base. Now, you see this relationship? We're going to rearrange this relationship just like we did up there for bicarb compared to carbonate ion and bicarb compared to H2CO3 for the molarity comparisons, concentration ratios for those species. Do the same thing here. Okay? So here's what I'm going to write. Sulfate ion over hydrogen sulfate ion equals hydroxide ion over Kb, pardon me, Kb. Hydroxide ion over Kb or Kb over hydroxide ion. What is it? When I divide something by this number, by way of magnitude, what will happen to the result compared to what I start with? It's going to be huge. We're letting these numbers talk to us. Dividing this by this number is just about the same thing as to take the value of this that I start with and multiply it by 1 trillion. What is this telling me then about finding hydrogen sulfate ion at an appreciable concentration in the solution? If the hydrogen sulfate ion that is present in the solution came from hydrolysis of sulfate ion. I'm not going to find any hydrogen sulfate ion in a solution that originally contained sulfate ion until I start making the solution awfully damned, fill in the blank, acidic or basic. Acidic. And I can assure you, when I dissolve calcium sulfate in water, at the minimum, the hydronium ion, at the minimum, when I dissolve calcium sulfate in water, the hydronium ion concentration cannot possibly be larger than what value when I dissolve calcium sulfate in water? 1 times 10 to the minus 7. Because the solution has got to be at least mildly basic. So, I repeat my question. Do I have to pay attention to the hydrolysis of sulfate ion if I want to calculate correctly the solubility of this stuff in water? No. KSP for calcium sulfate doesn't. So I'll take a look at the KSP value. Let's see. Yes. 9.1 times 10 to the minus 6. And so I'll write S. In this case, for sheetrock or calcium sulfate, will be the square root of this number. All right. Therefore, S equals. All right. Give me the square root of this number. Bingo. There we have it. Now then, we showed ourselves how to get the solubility of calcium sulfate in water. The number isn't very large, which accounts for the fact that calcium sulfate is not very soluble in water. Now let's go back to this issue of precipitation. Because what we're going to do is consider 0.10 molar sodium sulfate solution. We're going to imagine we have a solution containing sulfate ion at a 10th molar concentration of 2 sig figs. And we want to know how effectively we can find calcium ion if the sulfate ion is 10th molar. Thus, sulfate ion equals 0.10. So I'm going to go back to this, and I'm going to recognize that the solubility for calcium sulfate will be represented by the calcium ion molarity in this solution. Just like the solubility of calcium carbonate was represented by the calcium ion molarity in the calcium carbonate solutions we've looked at so far. So this will be S. What's this going to be? 0.10 initially. And what else? S. Now, tell me, we found S for calcium sulfate to be this in straight deionized water. We're now looking at the solubility of calcium sulfate in a water solution that has the sulfate ion fixed at 0.10, which tells us that the value for S for calcium sulfate in this solution has got to compare how to this number? Got to be smaller. So whatever the value is for S, if I know it's smaller than this number, when I add S to this, am I going to change this? No. So I now know that the solubility for calcium sulfate in a water solution that contains sulfate ion at a molarity of 0.10. Thus, S equals KSP over 0.10. Right? Because KSP is this molarity times this molarity. So algebraically, KSP is S times 0.10 plus S. And if S is so small that when I add it to 0.10, I don't make 0.10 get any bigger, because because I know S is smaller than this number. Then I got KSP equals S times 0.10. So if I want S, I take KSP and divide it by 0.10. That gives me 9.1 times 10 to the minus 5 molar. So this is telling me, if I have calcium ion in a solution, and I want to find out about its presence or absence by precipitation as the sulfate, and then I can find calcium ion. If the calcium ion molarity compares how to 9.1 times 10 to the minus 5 molar? Repeat. I've got a solution which may or may not contain calcium ion. I want to find out. And in the same solution, I've got sulfate ion at 0.10 molar. My 10th molar sodium sulfate solution. What has got to be the calcium ion molarity if the calcium ion is going to react with sulfate ion at a molarity of 0.10 and make a precipitate? What's the molarity of calcium ion got to be? It's got to be something that is bigger than 9.1 times 10 to the minus 5. That's what we just found out. Because S, which we just calculated, is the calcium ion molarity. Okay? So if I want to have an opportunity for a precipitate to form, then the calcium ion molarity multiplied times the sulfate ion molarity has got to be a number which compares how to KSP. If I want to have the possibility exist of calcium ion reacting with sulfate ion to make a precipitate, to make gypsum, to make sheetrock, so I can see this stuff, the calcium ion concentration multiplied times the sulfate ion concentration has got to compare how to KSP. I'm listening. Got to be bigger. Then I'll make calcium sulfate, or at least have the chance to do so. So we have proven that if sulfate ion is 0.10 molar, I can successfully find calcium ion, or have the chance to successfully find calcium ion in the same solution, provided the calcium ion is at a molarity which is larger than this. So we'll write over here, thus can precipitate calcium sulfate with sulfate ion molarity equal to 0.10 if calcium ion molarity is greater than, I'm running out of territory, this. I wrote this all down so you know what this means. Because if you don't know what this means, it's just a bunch of arithmetic on a piece of paper. Now, when we go to calcium hydroxide, there's the dissociation equilibrium. Do we have to pay attention to hydrolysis to get at the solubility for calcium hydroxide in water? Do we have to pay attention to hydrolysis? This is a stronger base than carbonate. Much stronger base than sulfate. Do I have to pay attention to hydrolysis? Yes or no? Yes or no? No, why not? When hydroxide ion hydrolyzes, when hydroxide ion reacts with water, what do I get? Water and hydroxide ion. I'm not changing the composition of the system at all. So I don't need to worry about hydrolysis here. Conclusion, I calculate solubility for calcium hydroxide from this equilibrium alone. Because hydrolysis of this, which takes place, but it doesn't change the composition of the system at all. So, KSP, calcium hydroxide, is memory 10 to the minus 5, something times 10 to the minus 5, 3.0. That's it. Let's see. Oh, where did I write you down? Here someplace. Ah, there it is. Okay, so far? Calcium ion molarity times hydroxide ion molarity quantity squared. That follows from the equilibrium reaction. Now let's tackle this so as to compute solubility. Have we not recognized that for solution containing calcium ion, and it's the solubility of the calcium ion containing salt that we're interested in, I can let calcium ion be the solubility. All right? So I'll write S. How does the hydroxide ion concentration compare to S? Twice. Because this material tells me when a mole of this goes in solution, beside putting a mole of calcium ion in solution, I put twice as many moles of hydroxide ion. So here's what I got. Now let's turn it into its corresponding algebra form. That's it. Nothing fancy about this. So 4s cubed is 3.0 times 10 to the minus 5. This gives me the solubility of calcium hydroxide in straight water. You can do the arithmetic. What will the magnitude of the result of this arithmetic? How will the magnitude of the result of this arithmetic? How will the magnitude compare to this? Greater than this. So which salt is easier to form? Which material will more easily form as a precipitate of calcium ion? Calcium sulfate or calcium hydroxide? Calcium sulfate. So if I'm going to try to find calcium ion in solution, and I have to choose between using sulfate ion or hydroxide ion, I'm going to pick sulfate ion. Now, what about calcium carbonate? Is it more easy to form calcium carbonate or calcium sulfate? That's a little more tricky because it depends on system pH. But if what I do is to take a solution that's got carbonate 10th molar, carbonate is fixed at 10th molar. I'm stipulating that it's 10th molar. If the carbonate is in fact 10th molar, is the original carbonate solution, the m sub I value for this, 10th molar? If carbonate is 10th molar in a solution, if in solution this is true, I'm stipulating this to be an equilibrium concentration for carbonate ion. If carbonate ion is in solution at 10th molar, is m sub I for this carbonate solution, like sodium carbonate solution, is it 10th molar? Is it 10th molar? Does carbonate hydrolyze? Does it hydrolyze to an appreciable extent? So is the label on the bottle 10th molar? It could be bigger than 10th molar. Point. If I take a solution that's got carbonate ion in it at 10th molar, so that I can compare it to hydroxide ion at 10th molar or sulfate ion at 10th molar. Which of these systems more readily finds calcium ion? 10th molar sulfate ion, 10th molar hydroxide ion. We just found that 10th molar sulfate ion does a far better job of finding calcium ion than 10th molar hydroxide ion. Because the solubility of calcium sulfate in 10th molar sulfate ion is a lot smaller than the solubility of calcium hydroxide in 10th molar hydroxide ion. But what about the solubility of calcium carbonate in 10th molar carbonate ion? What is the solubility of calcium carbonate in 10th molar carbonate ion? S, calcium carbonate in 10th molar carbonate ion. What is the solubility of calcium carbonate in 10th molar carbonate ion? KSP, calcium carbonate, 6.2 times 10 to the minus 9. What's the solubility of calcium carbonate in 10th molar carbonate ion? What is it? It's 6.2 times 10 to the minus 8, isn't it? It's just this divided by 0.10. Because if I stipulate that the carbonate ion molarity is 10th molar, then I've already said hydrolysis has already been taken care of. That's why we said the label on the bottle, whatever it is, has got to be bigger than 0.10 molar. You understand what we're doing here? Well, if you don't, you're going to follow up from this point tomorrow in discussion. Be there.